Everyone, I am Neeraj Ramtike, and today we will be seeing design and implementation of combinational circuits using Verilog. So first of all, let us see what is Verilog. So Verilog is a hardware description language (HDL) used to model and design digital circuits. It is widely used in the semiconductor industry for designing and verifying electronic systems. Verilog is a text-based language that allows us to design and simulate complex digital circuits. It provides a way to describe the behavior of circuits, its structure, and its timing. This is the basic syntax of Verilog code. The input wire A and input wire B are the input ports, while the output wire Y is the output port. The output port Y will carry the result of the expression. The expression is assigned here. Y is equal to A and B. The internal signal declaration. Wire temp declares wire signal named temp. The internal signals aren't directly accessible from outside the module. The behavioral description. Assign y is equal to a and b. This makes y as a result of bitwise and between inputs a and b. This was the basic syntax of Verilog. Let us further see what Verilog syntax parts are, that is gate level, data flow level, and behavioral level implementation with an example of parity generator. So first of all, let's see what a parity generator is. A parity generator is a digital circuit that generates a parity bit for a given set of input data bits. The parity bit is used for error detections in digital communication system. There are two types of parity generators, even and odd. Let us first see the even parity generator. An even parity generator is a digital circuit that adds a parity bit to a set of input data bits to ensure the total number of ones in even. This helps in error detection using data transmission. This is the logic circuit of even parity generator, and this is the truth table. Now let's see how we can implement this using Verilog. Using gate level implementation. Gate level modeling is only based on the logic gates. The input data we can see there is 2:0, that is for 3-bit data input, and output parity is for parity output. Wire P1 and P2 declares wire signal named P1 P2, and then XOR P1 data 0 and data 1, and XOR P2 P1 data 2. This assigns P1 and P2 as result of XOR data 0 and data 1 and P1 XOR data 2. This was gate level implementation based on logic gates only. Next is the data flow level implementation. The data flow level implementation describes the flow of data. Here you can see that the input and output port are assigned the same way as they were assigned in the gate level. The difference is in the behavior description. Let's see. In the gate level, we were assigning wires, and then we were giving the XOR expressions and assigning it to the output. Instead of that, in the data flow level implementation, we have directly assigned parity is equal to data, the symbol used to define or XOR. This shows as parity as the result of data 0 XOR data 1 XOR data 2. Now, let's see behavioral level implementation. And as you can see here, assigning the input and output ports are almost same and very similar to the earlier two, that is gate level and data flow level. But here you can see the difference. Here, there is no need to declare any kind of wire, and sensitive list the at asterisk change. This means that it is sensitive to all the signals within the block. This ensures that the parity bit is recalculated whenever the input data changes. Then parity is equal to data. This is the main part of our code. It shows that parity is assigned as the result of data 0 XOR data 1 XOR data 2. Now, we have seen the three types of implementation of Verilog, that is gate level, data flow level, and behavioral level implementation. Now let's see the result, that is the waveform implementation of this code. The first three are the inputs for the 3-bit and the last one is the output. We can see that the output changes from 0 to 1 whenever the input is odd. We just completed and saw how we can use the Verilog code to design and implement even parity generator. Now let's see how we can do it for odd parity generator. Firstly, what is odd parity generator? An odd parity generator is a digital circuit that adds a parity to a set of input data bits to ensure total number of ones is odd. This helps in error detection using data transmission. You can see that the logic circuit diagram is almost the same as even parity generator. The only difference is this NOT, which gives the exact opposite result for odd parity generator compared to the even ones. Now let's see how we can implement odd parity generator using Verilog code. Firstly, the gate level implementation. You can see it's almost the same as the even parity generator. The only difference this time is we have added the not parity P2. This assigns parity is equal to not of P2, keeps everything earlier the same. While in the data flow level implementation, we can see this sign. This sign denotes for not. And the behavioral level implementation, the same sign is followed, which used to define not. We can see the waveform result. The first three lines are the input and the last one is the output. See that the output is 1 whenever the input is even and it goes to 0 whenever it is odd. So today we have understood what is Verilog, its type that is gate level implementation, data flow level and behavioral level, and how we can implement combinational circuits like parity generator using Verilog. Thank you.